Hello students, welcome back to JCE Connect series of lectures. So in this particular lecture I will be solving a design problem uh, of welded connections. So in previous lecture we have been solved bolted connections. So in this particular lecture I will be taking welded connection design. So in this particular, I am considering a problem on a roof truss member. Generally, these kind of problems will be asked in exam. So I am taking that problem and designing the section here. The design problem given as design an unequal single angle section to act as a tie member of length 1.56 meter in a roof truss if it is to carry an axial load of 60 kN when subjected to possible reversal of stress into compression resulting from the action of wind or earthquake, design a welded connection. So this is the problem given here, and this type of problem generally asks for 15 to 20 marks. It is a design problem, completely you need to design. Here only the load will be given here. In this problem the load is given here, and nothing else given here. So taking that load, you have to first you have to calculate the area required. Then for that area you have to assign the section. Then after assigning the section you have to design the weld. Then after designing the weld you need to check the member whether it is safe or not. So here the first step will be, the first step is preliminary selection of section. So this preliminary selection of section will be uh, selecting based on the gross section yielding. So here I am taking preliminary selection of section considering gross section yielding. So as for the code IS 800 2007 page number 32, if you see page number 32, so there the formula is given as TDZ equal to TU, means the design load. The formula will be Az into Fy divided by gamma Mo. Taking this formula, we have used the same formula for the bolted connection also, that is the design of bolted connections of tension members. The same formula will be using here also. uh, Based on this one you have to calculate the area required. So here the working load is given, that is T. This is the working load given 60 kilonewton. You have to make it factor. So when you make it factor it becomes a design load. You have to multiply it by 1.5, sorry, 1.5, but multiply it by 1.5. So 1.5 into 60 it becomes a 90 kilonewton. This is the design load. For this load you have to select the section. Then after calculating the area required, so you will get a area 396 millimeter square. Just increase this area by 20%. You increase this area by 20% as a factor of safety. When you increase this area by 20%, the area becomes 475.2 millimeter square. This is the required area. Then in step number 2, what you have to do for the calculated area, so whatever the area is required, for that area you have to select an angle section, that is single angle, that to unequal leg, because it is mentioned in the problem you have to design unequal angle section. So you have to select unequal angle section from the steel table. Refer steel table and select an unequal angle section which is giving an area almost that is equal to, that is force equal to or more than the required area. So here let us try. I have selected ISA 60 by 40 by 5 mm, which was satisfying the required area. So I have selected 60 by 40 by 5 mm. Then the area of that section is 476 millimeter square. So it is equal to 475.2 millimeter square almost. That is a or it is just uh, greater than 476 millimeter square. So hence I have selected this ISA 60 by 40 by 5 mm. Then after selection of this angle section, just note down the properties of that angle section, and also remember you have to connect the longer leg to the gusset plate. Here you connect the longer leg to the gusset plate, and assuming gusset plate thickness as 8 mm. Gusset plate thickness is not given. You assume the gusset plate thickness more than 8 mm. So here I am assuming a gusset plate thickness as 8 mm. Then since you have selected the angle section, that is single angle unequal leg, so after that you just draw the figure showing that the leg is one leg is connected to the gusset plate. So here one leg is connected to the gusset plate. You can see here I mentioned that one leg is connected to the gusset plate, and also you mention CXX and EXX taking from the steel table. So I am taking the CXX and EXX. The CXX and EXX represents CXX represents the center of gravity of the section, and EXX represent from the center of gravity the extreme fiber distance. And outstanding leg also you mention here, that is a 40. Then the weld is been applied at the upper, that is at the toe as well as at the heel. Then this is the section I am showing this is the section, angle section. Then draw longitudinal section also. So this figure shows you the longitudinal section. This one is a longitudinal section, and in this longitudinal section the load acting here is TU, that is the design load. The design load we have calculated by taking a factor of safety, that is 1.5. We have got 90 kilonewton. That much load is acting through the centroid of the angle. Then mark LW1 and LW2 here. So these two lengths LW1 and LW2, we don't know, just you mark it LW1 and LW2, and the load acting here is a TU. Then to resist that TU, the load taking by LW1 and LW2, corresponding to LW1 the load is TU1, corresponding to LW2 the load will be TU2. These two are acting in weld. Okay, then the 60 millimeter is the width of the angle section. Width of the angle section, that is the leg size, and this 60 will be in tension area. Okay. Then after drawing this, just to keep ready this drawing, then you design the weld, that is design of welded connection here. Design of welded connection, that is step number 4. So in step number 1 you have to calculate the area. In step number 2 you have to uh, in step number 1 you have to calculate the area. In step number 2 selection of angle section, and in step number, this is step number 3, in step number 3 you design the welded connection. For design of welded connection, initially you have to assume the size of the weld, or else the size of the weld, as you know, in a welded connection it can be calculated based on the uh, edge conditions. If the weld is applying at the round edges or at the square corner, based on that you have to take the weld sizes, or else you are just assume the size of the weld initially. This one where I have assumed the size of the weld as 8 mm, then calculate the thickness of weld, that is thickness equal to 0.7 times of S. 0.7, this is for the fillet weld, and the fillet weld is applied at an angle of 45 degree. For 45 degree angle of fillet weld, the effective thickness becomes 0.7 times of S. Then you calculate the thickness. After calculating a thickness, so here one note I have mentioned here, since the load is not acting exactly at the center of angle leg, therefore the length of weld LW1 and LW2 varies. Hence, applying Varignon's theorem just to calculate uh, LW1 and LW2. Since it is an unsymmetrical case, we have seen in a welded connection how the unsymmetrical sections can be designed, that is LW1 and LW2. Okay, so these LW1 and LW2 are not equal because this is unsymmetrical case, that is sec, uh, the section is not symmetrical here. The load is not passing through this exact center of the angle leg, so LW1 and LW2 will be varies. Okay, then taking moment about A, so here I have mentioned two edges, edge A and B. Here I have marked edge A and B. Corresponding to edge A, the load acting is TU1, and corresponding to TU1, the length of the weld will be LW1. So LW1 is taking a load of TU1, and LW2, that is at B edge, corresponding to LW2, the load is TU2, means LW2 length load is taking TU2. TU1 plus TU2 will be TU. Now you have to take the moment about A. Then when you take moment about A, here TU1 into 0, which is passing through the moment center, TU2 into 60, then TU equal TU into EXX. Then substitute the value of TU, then TU2 is unknown, into 60, that is here TU2 into 60 about moment edge A. I am taking moment about A. TU2 into 60, then TU1 passing through the moment center, that is A, TU1 into 0, then this TU into EXX, TU into EXX, that is 40.5. You will get this one. Okay, then you will get TU2. You will get, sorry, you will get TU2. You will get a TU2 as 60.75, 60.75 kilonewton. Then after calculating TU2, the TU1 can be easily calculated. Once you get TU2, TU2 will be what? TU minus TU2. You will get a TU1 here. TU1 will be TU minus TU2. You will get a TU1. Then TU1 plus C2, if we add, again you will get a 90 kilonewton. Okay, then here we got the load taken by the LW1, or the load taking by the LW1 and load taking by the LW2 corresponding to TU1 and TU2. Corresponding to TU1, the length required is LW1. Corresponding to TU2, the length required is LW2. So once we know this TU1 and TU2, the length can be easily calculated. To calculate the length, we need to calculate the length of weld per millimeter run. Means per 1 millimeter run of weld, what is the strength of the weld? Because strength we know each side, that is TU1 and TU2. If we calculate strength of weld per millimeter run, then the LW1 will be TU1 by unit strength of weld. LW2 will be TU2 divided by unit strength of weld. To calculate unit strength of weld, so that is formula we are having, Fu divided by root 3 gamma mw into LW into T. Then here LW can be taken as 1 millimeter run. Here I mentioned here LW is 1 millimeter. Thickness we have calculated already 5.6, and gamma MW, that is assuming the shop welding, 1.25. Then substitute here, you will be getting a unit strength of weld, that is strength of weld for 1 millimeter run 1060.47 Newton per millimeter. Once we know the unit strength of weld, then the length of weld on one side, that is LW1, will be TU1 divided by PUW. When you substitute here, you will get 27.58 mm, say 30 mm. Similarly, LW2 will be TU2 divided by PUW. You will get 57.28, say 60 mm. So this is very simple. So once you get LW1 and LW2, you know the section, means you have been selected the section. For that section you have to apply the weld here, LW1 and LW2. This is the length of the weld. On this figure you have to mark that length of the weld. Okay, here you have to mark LW1 and LW2. Then after marking, you have designed the weld now. So after designing the weld, you need to do the checks. So as you know, the welded that is a tension member will fail in three modes of failure, that is strength in yielding, strength in rupture, and strength in block shear. So in three modes it fails, so we need to check that all three modes of strength. So if we check if the section is passing in all the three modes, then the assigned section is safe and also the connection details are safe. If anyone fails, we need to revise the section. So this is same as bolted connections. Okay, so all the procedure is remain same even for welded and bolted connections, both the procedures are same. So here the first check we need to do is check for strength in yielding. So you have to refer IS 800 2007 page number 32. In that page, the check for strength in yielding, the formula is given TDZ equal to AZ into Fy divided by gamma MO. So here AZ you have to substitute the provided angle area into 250 is the yield stress divided by partial safety factor for the material, that is 1.1. When you substitute all the values and calculate, you will be getting the load as 108.18 kilonewton, which is more than 90 kilonewton given load. Hence the section is safe in yielding. The next check you need to do is check for strength against rupture, that is TDN. So to calculate TDN, we have a formula for TDN, 0.9 ANCFU divided by gamma ml plus beta AZO into Fi by gamma MO. Again, if you refer IS 800 2007 page number 33, you will be having this formula. So I'll show you that one page. Sorry, I'll show that page. So this page, this formula you're having, for single angles, the rupture strength of an angle connected through one leg is affected by a shear lag. The design strength TDN as governed by rupture at neck section is given by. So this formula is given, TDN formula is given. Please look at this formula. The formula is given as 0.9 ANCFU divided by gamma ml plus beta AZO Fi divided by gamma MO, and beta is a correction factor, that is for shear lag. When the one leg is connected to the gusset plate, there will be unequal stresses will develop after applying the load. To take care of that unequal stresses, this is the correction factor given in the code. So refer this formula and calculate all the values, substitute here and get TDN. Okay, so this is the formula given. Even block shear strength due to block shear formula also given here. So even TDZ also given in IS 800 2007. This formula we have taken for checks. Even TDN. Then this is how to take the block shear and uh, length of the weld, that is LC, how to take. So this is the ball strength due to block shear formula given in page number 33 IS 800 2007. Refer and calculate the strength. So here the TDN formula, I have taken the same formula which was given in IS 800 2007. Then you go on calculating each one, that is ANC, AZO, FU, gamma ml. ANC is what? Connected leg area. Here I have shown a figure. Just please look at the figure. I written connected leg and unconnected leg here. So what is the connected leg area and what is the unconnected leg area, and how to calculate the connected leg area and how to calculate the unconnected leg area, I explained in my earlier lecture. So please refer that lecture and calculate the area here. So connected leg area, that is ANC, I have calculated here. Then unconnected leg area also I have calculated here. Then you calculate the beta value. So you know, you are very familiar with this, how to calculate beta value and all, because we have solved many problems in earlier lecture. So please refer that and calculate the beta value here. So here the change here compared to bolted connections. So W is again the same, the outstanding leg width you need to take. T is the thickness of the plate. Fy will be the yield stress. Fu will be the ultimate stress of plate. And Bs, you need to take Bs. So I'll show you here, which is given in a code book. See, look at this figure. So Bs is W. Okay, so whatever the outstanding leg is there, so you have to take that as a W. This is outstanding leg and this is the connected leg where the weld is been applied, that is the connected leg and outstanding leg. Okay, Bs equal to W. And for a bolted connection, Bs will be W plus Wi minus T. Okay, so here taken Bs is equal to W 40. Then calculate LC. LC will be, in bolted connection we have taken the center of first bolt hole to the last bolt hole along the direction of load acting. So here the connection is weld, the connector is a weld, and you have to take the average length. We have calculated the length of the weld, that is LW1 and LW2. So you have to take the average of that 30 plus 60 by 2, you will be getting LC. This is LC. Substitute all the values in beta, you will be getting a beta value as 1.097, which is more than 0.7, that is a check. Then substitute all the values in TDN, you will be getting a TDN as 130.48 kilonewton, which is more than 90 kilonewton, hence safe in rupture. So it has passed in second case also. Okay, next, third one is check for block shear strength. As I mentioned earlier, this formula is also given in IS 800 2007 at clause 6.4.1 page number 33. If you refer, you will be getting this formula where they mentioned the block shear strength TDB of connection shall be taken as the smaller of following. So these two formulas are given, TDB1 and TDB2. The same formulas are being used in bolted connection also. You have to use the same formula for welded connection also. Again you calculate AVZ, AVN, ATZ. ATN, AV is the shear area, ATN is the ATZ, and ATN are the tension plane areas. Again the shear plane areas to be taken along the direction of load, that is parallel to the load, and the tension area to be taken perpendicular to the load. So in this case the shear area here, I'll mention you. So this is the shear area, this one is the shear area, this one along the direction of load. To calculate LV, you have to take this plus this, LW1 plus LW2 into thickness, that is the shear area, and this part is a tension area, this one is a tension area perpendicular to the load, this and this is shear area. I hope you understood this one. Then so you calculate shear area, that is a gross LV into T. So I have taken 30 plus 60 into T, and into T, that is you have to multiply by gusset plate thickness, not the angle thickness, because the weld is, angle is been connecting to the gusset plate. So gusset plate thickness to be taken here while calculating AVG and AVN. Okay, AVG comes out to be 720 millimeter square, and again AVG equal to AVN, that is a net area also comes same, because here the connector we are using as a weld, there is no question of making any holes in the uh, pl plate material. So AVC equal to AVN, then ATC will be what, tension area. So tension area is LT into T, that is 60 into 8, 480 millimeter square. Then substitute all the values in TDB1 and TDB2, you will be getting a TDB1 236.17 and TDB2 190.89 kilonewton. So the least value of these two, that is 190.89 kilonewton, will be the block shear strength, which is more than the load given, that is 90 kilonewton, hence safe in block shear strength also. Okay, so it has passed in all the three cases, hence the assigned section is safe in carrying the load, hence this is the uh, design. Okay, suppose if anyone fails in during checks, if anyone fails, either means yielding or rupture or a block shear, then you have to revise the section, you have to redesign the things. Okay, and one more mentioned in the problem, the length is given, length of the member is given. So the reason, you have to check the slenderness ratio of that particular uh, member. So what happens in a tension members, in worst possible cases, if during wind, if the during a wind or earthquake happens, then all the forces in the member may get changed. The compression may become a tension, or tension may become compression. So in that case, the reversal of stresses will takes place. So for that reason, you need to check the slenderness of the member. To check the slenderness of the member, lambda equal to KL by R minimum, and this slenderness uh, the in IS 800 2007 it is given. So that is show here. So here it is given the maximum effective slenderness ratio. In page number 20 it is given the maximum effective slenderness ratio KL by R minimum. Values of a beam, strut or a tension member shall not exceed those given in a table number 3. KL is the effective length of the member and R is the appropriate radius of gyration based on the effective section as defined in 3.6.1. So in table number 3, some of the values given, that is for maximum effective slenderness ratio. So here they mentioned a member carrying compressive loads resulting from dead loads and imposed loads, that is 180, that is for compression. And for our case they mentioned this one, a member normally acting as a tie in a rope truss or a bracing system not considered effective when subjected to a possible reversal of stress into compression resulting from the action of wind or earthquake forces. When the high speed wind blows or the earthquake happens, the tensile force may become a compression and the compression may become a tensile. That is, a reversal of stresses will take place. In that case, the slenderness of the member, that is, the slenderness ratio of the member, should not exceed 350. It should lie well within the 350. So now we need to check with respect to this what is the slenderness ratio of the assigned section now. Okay, now you have to check that last one, slenderness ratio KL by R minimum. KL is the effective length. The length given here is a 1.56 meter. Convert into a millimeter, that is 156 millimeter. KL and 0.85 to be taken effective. K equal 0.85. Then effect, this is the effective length. Then R minimum from the steel table, you have to refer steel table for the assigned section. You have to get RXX, that is R minimum. You have to take R minimum to taken the minimum of RXX, RYY and RUU, RVV. So out of this, whichever is the minimum that is to be taken, that is the radius of gyration. So now substitute here and get the slenderness ratio. Here I am getting a slenderness ratio as more than 156, which is less than 350. So please make a correction here. It is a less than 350. So this is less than 350. This one less than 350. Right? This is less than 350. Hence it is safe. The maximum slenderness ratio for the member normally acting as a tie in a roof truss is 350. Hence it is safe. Hence at last you have to write one line. Hence provided angle section, that is ISA 65 by 45 40 by 5 is safe, and also the connection also safe. Okay, so this is the design problem. So this is the way to solve the design problem. Step by step you just solve the design problem. So the problem will be given like this. For usually for 15 to 20 marks direct question you will be getting in exam. So in this problem they given the single angle section design and they mentioned unequal angle to be selected from the steel table. You have to design unequal angle, and sometimes what they mention design and single angle section. In that case you may select equal angle or unequal angle section. Since they are mentioned here unequal angle section, so I have been selected unequal angle section and designed the section. Okay, and this is the welded connection. So step you solve step by step, then you will get the marks step by step. Okay, like this. So let us take one more problem of double angle section. So double angle section, I'll take a double angle section, one more problem. So in this again the same welded connection only. Problem on design of welded tension member taking double angles. Okay, so means here they given design a tie member using a double angle, and they mentioned in the bracket equal legs, means you have to select equal angle, that to double angle section, connected on either side of a gusset plate, subjected to a force of 300 kilonewton. Use suitable welded connection. If the length of the member is 3 meter, check for reversal of stresses. See, you have to remember, if the length of the member is given in a problem, it means you need to check its slenderness ratio. As I mentioned earlier, and I shown you which phase to be referred in IS 800. With respect to that, you check the slenderness ratio of that particular section, means whichever section you assigned. Okay, so if you leave that step, again you lose your marks, around 5 marks you will be losing. So again you follow the steps. step number 1, you have to assign the preliminary section. Same in the same way you have to means as you have solved in the previous problem. Likewise only you have to design. You have to first calculate the preliminary section required considering gross section yielding as per the IS 800 2007. Okay, just you go through this one, you calculate the preliminary area required, then you increase that area by 20%, and whatever the area you get after increasing 20%, assign the section for that area. Means you select the section from the steel table. Okay, so here the selection of angle, refer steel table and select double angle. Okay, because they asked you to design a double angle, equal legs means equal angle to be selected. And let us try this area, let us try 100 by 100 by 8, and this section is giving, I have selected the double angle. I have selected double angle, and double angle area will be 2420. So you have to refer steel table and you have to select a double angle, because double angle section is been asked here for the design. So you have to take the double angle area. This much area is giving that the assigned section 2420 area. After that one, just to draw the figure like this and mark the angle size, that is the leg sizes 100 and EXX CXX, that also take from the steel table mentioned here like this how I have mentioned. Then the length of the weld, length of the weld on either side LW1 and LW2. Then the load is given, that is 300 kilonewton, make it factor, it becomes a 450 kilonewton. For the 450 kilonewton you have to design the double angle section. So after drawing this figure, then design the welded connection. So again assume the size of the weld. After assuming the size of the weld, calculate the thickness. Then since it is unsymmetrical case, take moment about any one end, either end A or end B, then calculate TU1 and TU2 like earlier case. Just to calculate TU1 and TU2, then after calculating TU1 and TU2, you will get the LW1 and LW2. So before calculating TU1 and LW1 and LW2, you have to calculate the strength of a 1 millimeter weld. Then calculate LW1 and LW2. Once you get a LW1 and LW2, then mark in this figure LW1 and LW2. Then whatever the LW1 and LW2 you get, then you have to go for checks. That is check for strength in yielding TDZ, then check for strength in rupture and block shear. So what is the change here? So in check for strength in yielding, directly we take the area for double angle only. AZ we substitute double angle only. Okay, then directly whatever answer you get, you write it. But for TDN and all, so for TDN and all, as I mentioned in code here, this TDN, what they mentioned here in code, single angles, the rupture strength of an angle connected through one leg is affected by shear leg, and this is the formula we are having to calculate the TDN, that is rupture strength, and this formula is for one angle. If suppose double angle you are designing, since you are designing a double angle, you have to multiply it by 2. Whatever the strength you get, you have to multiply it by 2. Why you have to multiply it by 2? Because you are designing the double angle. So whatever the formula it is given in a code, that is for a single angle, since the double angles are been providing here, you have to multiply it by 2. Whatever the strength you get, you have to multiply it by 2. That is the change when you compare with single angle. Okay, calculate TDN. Then the TDN what we get, 847.89 kilonewton. See, it is too much on higher side. Anyway, it is safe, it is passing. That is the low given load is 450 kilonewton, and hence it is safe. It is too much on higher side. So while choosing also, you have to choose judicially. That should not become more uneconomical side also, since the load acting is 450 but the assigned section is giving 847. Anyway, it is safe. Then check for a block shear strength. Again, I refer IS 800 2007, clause 6.4.1, page 33. Calculate TDB1 and TDB2 like earlier uh, case. So again, as I told, since you are designing double angle, you have to multiply it by 2. That is a change. You have to multiply it by 2. Calculate AVG and AVN. ATZ, ATN. AVG is the shear area which is to be taken parallel to the load, and ATZ is the tension area which is to be taken perpendicular to the load. So how to calculate these AVG and AVN, ATZ, ATN I already explained in earlier problem, and even welded connection also I explained. So please refer that one and calculate AVG, AVN, ATZ, ATN, substitute in TDB1 and TDB2. Then after substituting, then you, whatever the strength you get, you multiply it by 2, since we are providing or we are designing double angle, hence you have to multiply it by 2. Then you will get the strength, that is TDB1 and TDB2. The TDB1 and TDB2 you obtained as 1559.88 kilonewton, which is too much on higher side, is 450. Again, the TDB will be the least of TDB1 and TDB2. Anyway, it is more than 450 only, hence safe. Okay, then again, the length of the member is given here. They are asking you to check the slenderness ratio for the reversal of stresses acting in a member. So again, the same way, you have to refer that code. In a code table number 3, the maximum slenderness ratios are being given. With respect to that, calculate what is the slenderness ratio of this assigned section. So I have taken KL by R minimum. KL is the effective length to be taken 0.85 times, that is 85% of the length. Then R minimum will be minimum of RXX and RYY. Here only you will get a 2 axis, that is RXX and RYY. So take it from steel table, which is least out of these two. You take it as R minimum, substitute here, then you will be getting a slenderness ratio, and 83.06 is the slenderness ratio, so which is less than 350, hence safe. So this is the design problem for the welded connections. Okay, I hope you understood these two problems. So I'll be giving some assignment, so please solve those assignment. You try to understand. If you get any doubt, you can uh, call me or text me. Okay, thank you.